Wow, so many beautiful faces. All right, I'm Angelo. I work with RISC Zero since more or less 1.5 years. I might give you a little bit of background about me. I mainly work in academia doing research prototypes. Typically, I haven't really dealt with user-facing issues when using our solution. So I feel like since I joined RISC Zero, this particular topic has been really important for us, and I am also learning how to improve on it. And I think this, especially this event is very important and kind of matches one of the main goals that we try to achieve at RISC Zero, which is basically trying to make all of these amazing solutions that we are all working accessible, more accessible to developers, because we want, at the end of the day, make them more creative, right, without getting crazy into too many technical details about circuit or the likes, right? Anyway, so enough with the chit chat. Today I'm going to introduce you this library that we have been working internally at RISC Zero, and now is already released. And it's about making a little bit better experience when it comes to using and integrating a ZK coprocessor in your application, right? So I don't know how many of you are familiar with, well, a ZK coprocessor, but there are different definitions that you can find, I don't know, online, on Twitter, whatever. It doesn't really matter. I think that one of the main goals of the ZK coprocessor in general is to minimize the cost, right, of on-chain computing. So if you have a smart contract on Ethereum, right, you want to maybe take the most expensive side of the computation and send it off-chain to your ZK coprocessor so that it's going to compute for you. And then you take back the verifiable result, right, that you can push again back on-chain, verify that obviously is correct, and then save some gas, right? And that would hopefully, aside from saving you some money, I guess, also unlock new type of applications. And so, if there is like one takeaway of this from this talk, will be exactly try to answer this question. So, can we then unlock provable smart contract execution, right? Before answering this, though, when it comes to offloading computation, of course, there is also a part of that regards data, right? Data that might be on-chain. So you don't only want to offload the computation as it is just for the sake of computing whatever function, right? But you also want to combine some logic with some data that are on-chain. You might want to prove something about those, right? So how can we probably access on-chain data from a ZK coprocessor point of view? Well, we are lucky, at least in the Ethereum context, because we have this nice RPC method called ETH get proof, which is basically the standard for querying a full node, or most likely also an archive node, about any account or contract storage that you might want to know, right? Basically, this RPC method will give you a sort of proof of inclusion, which is a bunch of hashes that then you can hash together and then prove the inclusion of a given value, right, with respect to the state root of a given block number. And to kind of understand a little bit more how you can make use of such a method, would be worth spending maybe a minute explaining how storage is basically represented in a contract when it comes to the EVM, right? So you have this very elaborated contract that I personally wrote here, right? I might also have copied from some documentation. Anyway, so you have this contract with the 3 state variables A, B, C. These are really super easiest example because they are statically sized, so should be pretty straightforward. At compilation time, this variable gets basically assigned a slot index that maps, right, a certain position on this mapping to their respective value, right? So you have your smart contract, you have your variables. They can be statically sized, they can be dynamically sized. When they are dynamically sized, more complicated data structure, things get a little bit more complicated. But in general, in order for being able to use this ETH get proof method, you really need to know how to find these keys, this slot index. And my first programming language that I felt in love with was C. So I'm kind of used to, going low level and having to deal with pointers and having a tough life, I guess, in general, when it comes to this sort of details. But I guess if you are a developer that just care about, writing your nice application, you might also not have the time to do it, right? You don't want to get crazy. You have other things to take care of. Luckily, there are some tools around that helps you find those values. So we have evm.storage, assuming your contract is already on Ethereum mainnet. That only works with that. Or you have this also super cool tool called Forge Inspect, which is part of the tooling family from Foundry, that instead assumes that you have the smart contract copy on your local machine, right? And then, yes, and then you can find your slot index and use those together with the ETH get proof. Now, to kind of give you a recap of this recipe, how you could basically unlock proof storage, right? Proof of storage. You first find these all the required storage slots that you need, right? To basically get the data that you want to combine with your computation in your ZK coprocessor, again, to save some gas on Ethereum. Then, for each of those, you call the ETH get proof. Yeah, there is like a typo there, but it's just get proof for a given block number. And then, finally, the most important bit, I guess, is that you need to generate a ZK proof of the verification, right, of all of these proof of inclusion given by the ETH get proof against whatever state root of the block number that you basically started all the query from, right? And if all of these sounds familiar, it's because it should be familiar. Out there are already some really, really cool projects. I'm going to just cite them, a few, right? Not all of them. But there are really a good bunch of projects that uses this sort of technique. We have Axiom, we have Brevis, but there are also others. And they basically allow you to have access to on-chain data on whatever ZK coprocessor, right? Now, again, going back to trying to make the life of, in this case, Solidity developer, right, easier. Is there something better we can do? So one natural question will be, why can't we just query, the Solidity function directly? Why do we need to go so much low level? And that would be ideal, obviously, right? But in order to achieve that, what we will need to do is to prove the execution of a given smart contract function in the EVM, because those functions, they need to run in the Ethereum virtual machine, right? And it turns out that it should be trivial if you are able to run the EVM within whatever ZK VM, in our case, our RISC-0 ZK VM, that's possible. So that is basically an example of how one developer could use this library that we developed, the view called proof library. And it's pretty straightforward, I would say. At the beginning, let me maybe highlight this. Let's say that you want to prove the balance of some address with respect to whatever contract that there is deployed on Ethereum, right? I think in this example we are using the USDT contract deployed on Sepolia, but we will go there later. Anyway, so the ERC20 make you available some function, obviously. In this case, we do care about the balance of, and this is the signature that you can literally copy and paste from any ERC20 contract, right? Which the only argument it takes is the address, the account of which you want to know the balance, and then it returns, hopefully, the balance that you might hope to be greater than 0 if it's yours or something like that. Anyway, aside from defining the signature, then you need to prepare the call, right? So you will basically fill in the argument of your view function, in this case the balance of, with the address that you care about, knowing the balance of. And then you need to basically say, okay, which contract I want to query, right? So in this case, we are querying the USDT contract deployed on Sepolia. I think so, if not mistaken. And that's more or less it. Now, this snippet is basically more or less everything you need to run in your guest code of the ZK VM. So basically, this is the code that will be executed to generate the ZK proof. And it's super straightforward. We will go maybe step by step in a few minutes also, especially for the beginning part. But just to give you an idea, at the beginning you read the input from the environment, which is a sort of channel that you have between the guest running the code that is going to be proven, and the host side, right, which is typically outside of the ZK VM that is there to basically provide input and start basically the prover. And then we have the validation happening of all of these input. Basically, the input is we will talk about it later. Let's, for now, just stick to the input that you need. It's basically the information that the EVM will need to know in order to execute whatever view call you want to execute, right? So you validate then. Basically, the validation is validating all the proof of inclusion of all the storage slots that are involved during the query that you need to perform, right? And then you can definitely commit to the block hash and block number with respect to the data that you used. This is going to be super useful then to validate the proof, right? And the most important, I guess, point is that then in order to execute the call, you just execute it, right? And that's it. So just to spend a few words about how this actually works. If you remember at the beginning, I said the guest access the input, right, from the host. What it happens in reality is that the host will run a so-called pre-flight phase, which is basically running for you the view call, calling basically the RPC node of Ethereum, right, with the function that you want to query. In our case was the balance of, right? And what is going to happen is that it will use this as special cache DB that is going to cache all the storage slots that are basically involved during this query. So you basically, that is the trick to strip you away from having to deal with the details of finding the storage slot, because querying the node will basically give you all of what you need. And then for each of the storage slot and accounts that have been involved during this query, we make use of the ETH-GetProof RPC method to get the proof of inclusion for each of those. And that is basically the part of the input we were talking about here, right? So here you basically have a sort of cache DB that the EVM will then use. But before using it, you need to make sure that all of the information has the right integrity, right? So you basically do this into AMP, which basically is running the proof of inclusion verification for everything, right? With respect to the block hash and block number and the state root that you are committing to. And yeah, so basically you verify the storage integrity, and then you run your Solidity function on the EVM inside the ZK VM. That's it, right? This is super cool because we kind of started working at this view call library just for the sake of view calls, but they are typically in Ethereum, you know, all the functions that do not touch the state are called view because you are just viewing, right? But to be honest, at the end of the day, you are running an EVM inside your ZK VM. So you don't really have any sort of limitation also of running any type of Solidity code. Let's say that you spent a lot of money auditing already your contract. And of course, you can translate some of the heavy part in Rust or in whatever other language and use whatever other ZK coprocessor and then combine that with, you know, the more classical proof of storage. But, you know, that requires time, requires resources, so you might be more happy, I guess, just using your own audited code and ZK proof that, right? The example that we saw before takes roughly 6 million cycles. And I say roughly because there are some, when you do a balance of query, there are a few things that by default get also retrieved. For instance, there is the Coinbase address that is always loaded. There is also the address, the account address of who is going to get the reward, which are by default, right, part of any of this query, but for the sake of proving this, they are not really needed. So you could totally strip those out and get this number down even more just by doing that. And in any case, this takes sort of like 30 seconds if you use a very nice GPU. And by very nice, I mean something that I would also personally dream to use when playing video games, like a 3090 Ti. But still, we are talking about consumer GPU, right? And also, there are really a lot of optimization here yet. We nowadays, I don't know if you are looking Twitter, but like every day it's like an announcement of massive improvement on performance, which is super, super nice. I'm super happy about the space moving so fast. But it also tells you that numbers nowadays, they are super cool, they are super exciting, but they will all go down. They will all improve, right? And the same is for our ZK VM, right? Just to make an example, as soon as you connect a catch accelerator to this, will massively drop the number of cycles required to run this sort of example. Regarding also scalability of this approach, we tested loading up to 100,000 storage slots on a single call, which is a lot. And to give you an idea, you could even use it to call a view function that calls a view function, that calls a view function, that calls a view function 1,000 times, so that you wouldn't even be allowed to do it on Ethereum because you would run out of the maximum gas that you can fit within a block. So this literally can be used to unlock application or way to interact with the chain that wouldn't be possible with that ZK coprocessor, right? And I'm super happy about it because if you remember, one of the goals of the ZK coprocessor was, aside from saving gas, also allow to unlock new applications, right? Now, obviously, this is the first iteration of the library. right? So we do have still some limitation, especially when it comes to validate the proof on chain. So to give you an example, in our example, we use the block cache opcode that we basically use to compare the latest 256 blocks. That opcode is basically, this is what is going to give you on Ethereum, right? Access to the latest 256 blocks that you can use then to compare to what you have committed on your proof, right? If you remember here, we commit to the block hash and block number. So that means that then if you use this trivial validation, you have basically, well, around 50 minutes from the moment you start the proof to the moment you have to publish it, right? Now, obviously, there are a number of trivial improvements to solve this limitation. You could just, save, like add some state about older blocks, or you can just have a proof that basically chain such that, you can prove that a previous block is containing a more recent block, and so on and so forth. There are really so many approaches you can do. But the cool thing is that this library is open source. I'm dumb and I forgot to add the link, but it's basically on the RISC-0 repository. So yeah, please check it out.
Thank you, Angelo. Thanks for making life easier for the devs. Let's see if you will receive questions from the audience. Yes, please.
Hey, Angelo, thank you so much for the presentation.
Hello, my friend.
Please tell me what about the verification cost and actually how much real proofs can be executed on chain during the one goal with help of zero, of course.
Yeah, absolutely. Like the verification cost on the Ethereum side is mostly dependent on the verification of Agro 16. If you really want to just verify your proof. So it's around about 200K of gas for verification, a little bit more, right? It really depends. But we are around 200K of gas. But that doesn't really include the idea of then using aggregation. Like nowadays, we are talking about aggregating so many proofs. So that would mean that you can aggregate a bunch of proofs so that you basically share the cost of one single verification of Agro 16, and then your own application can just use a very trivial proof of inclusion against the root, right? If you recursively prove all of the aggregation, and then you just make sure that your journal, your result is part of the tree, right, of this aggregation. So that will come down even more the cost of using it.
And the real amount of proofs, how much storage proof can be like? I saw 1,000K. It was.
You are super welcome to try because we haven't had the time.
Okay.
To test
Thank you so much.
But
yeah, sure.
Yeah, sure. It's super cool.
Thanks. Thank you for your question. Okay. Thank you, Angelo.
Yeah, thanks to you guys.